The conductor connecting the 25 amp fuse inside the control panel to the remote heater is classified as a branch circuit conductor. To understand why, it's crucial to define these terms within the context of electrical wiring. Let's clarify each term. Firstly, a feeder. A feeder is defined as the circuit conductors between the service equipment or the source of a separately derived system and the final branch circuit of a current device. In simpler terms, it's the wiring that carries power from the main electrical panel or transformer to a subpanel or distribution point. Secondly, a tap conductor. A tap conductor is a conductor that originates from a feeder and supplies power to a single overcurrent protective device. Tap conductors have specific requirements outlined in the National Electrical Code Section 240.21 regarding their length and ampacity relative to the feeder they tap from. These requirements ensure safety and prevent overheating or fires. Thirdly, a branch circuit conductor. A branch circuit conductor is defined as the conductors between the final overcurrent device protecting the circuit and the outlet or load. In this scenario, the 25 amp fuse located inside the industrial control panel serves as the final overcurrent device protecting the heater circuit. Therefore, the conductor running from the load side of the 25 amp fuse to the remote heater is indeed a branch circuit conductor. The 12 American wire gauge tap from the power distribution block to the 25 amp fuse being less than 10 feet adheres to tap rules found in the National Electrical Code. These rules specify conditions under which smaller conductors can be tapped from larger feeder conductors, provided certain protection and length requirements are met. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for safe electrical installations. Understanding and adhering to the NEC is crucial for electrical engineers, electricians, and anyone involved in electrical work. The NEC covers various aspects of electrical systems, including wiring methods, overcurrent protection, grounding, and equipment installation. When dealing with electrical circuits, several factors must be considered to ensure safety and proper operation. Firstly, ampacity. Ampacity is the current carrying capacity of a conductor expressed in amps. The ampacity of a conductor depends on its size, material, insulation type, and ambient temperature. It's essential to select conductors with sufficient ampacity to handle the expected load current to prevent overheating and potential fire hazards. In this case, the 250 NCM wire has an ampacity of 255 amps, which is suitable for the 250 amp circuit breaker. The 12 American wire gauge tap has an ampacity of 25 amps, which matches the rate of the fuse it feeds. Secondly, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow caused by overloads or short circuits. These devices interrupt the current flow when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of electrical fires. The 25 amp fuse provides overcurrent protection for the heater circuit, ensuring that the conductor and heater are protected from excessive current. Thirdly, voltage drop. Voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Voltage drop can be calculated using Ohm's law and the conductor's resistance per unit length. Fourthly, grounding. Grounding is the process of connecting electrical equipment and systems to the earth, providing a low impedance path for fault currents to flow back to the source. Grounding helps to protect people from electric shock and reduce the risk of electrical fires. Grounding systems must comply with the requirements of the National Electrical Code, including the use of grounding electrodes, equipment grounding conductors, and bonding jumpers. When working with industrial control panels, it's essential to follow safe work practices and use appropriate personal protective equipment. Firstly, the energized circuits. Before working on any electrical circuit, always energize it by turning off the circuit breaker or disconnecting the power supply. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Secondly, lockout-tagout. Use lockout-tagout procedures to prevent accidental re-energization of circuits while work is in progress. This involves placing a lock and tag on the circuit breaker or disconnect switch to indicate that the circuit is being worked on. Thirdly, wear personal protective equipment. Wear appropriate personal protective equipment such as safety glasses, gloves, and insulated tools to protect yourself from electrical hazards. Avoid wearing jewelry or other conductive objects that could come into contact with live circuits. Fourthly, follow National Electrical Code requirements. Ensure that all electrical work complies with the requirements of the National Electrical Code and any applicable local codes or regulations. This includes proper wiring methods, overcurrent protection, grounding, and equipment installation. Fifthly, inspect equipment regularly. Regularly inspect electrical equipment and systems for signs of damage or wear, such as frayed wires, loose connections, or cracked insulation. Replace or repair any damaged equipment immediately to prevent potential hazards. Now let's consider some examples of applying these concepts. Example 1. A 20-amp circuit breaker supplies power to a lighting circuit in a commercial building. The conductors running from the circuit breaker to the light fixtures are branch circuit conductors. The ampacity of the conductors must be at least 20 amps, and the voltage drop should be limited to 3%. Example 2. A 480-volt feeder supplies power to a subpanel in a manufacturing plant. The conductors running from the main electrical panel to the subpanel are feeder conductors. The ampacity of the conductors must be sufficient to handle the total load of the subpanel, and the voltage drop should be limited to 5%. Example 3. A 14 American wire gauge tap conductor is used to connect a small control transformer to a 20-amp feeder. The tap conductor is less than 10 feet long and is protected by a 3-amp fuse. This configuration complies with the tap rules in the National Electrical Code. When designing and installing electrical systems, it's essential to consider the specific requirements of the application and the applicable codes and standards. This includes selecting the appropriate conductors, overcurrent protection devices, grounding systems, and wiring methods. By following these guidelines, you can ensure that electrical systems are safe, reliable, and efficient. In summary, the conductor running from the 25-amp fuse inside the industrial control panel to the remote heater is classified as a branch circuit conductor. Understanding the definitions of feeders, tap conductors, and branch circuit conductors is crucial for proper electrical system design and installation. Always adhere to the National Electrical Code and other applicable codes and standards to ensure safety and compliance. Remember to energize circuits. Use lockout-tagout procedures, wear personal protective equipment, and inspect equipment regularly to prevent electrical hazards. This knowledge is essential for anyone working with electrical systems, from electricians and engineers to maintenance personnel and homeowners. By understanding these concepts and following safe work practices, you can help to ensure the safety and reliability of electrical systems. Furthermore, it's important to stay updated on the latest changes and updates to the National Electrical Code, as it is revised and updated every 3 years. This ensures that you are using the most current and relevant information when designing and installing electrical systems. Continuing education and training are also valuable for staying up to date on industry best practices and new technologies. By investing in your knowledge and skills, you can enhance your ability to work safely and effectively with electrical systems.